Good evening everyone. Just quickly confirm audio video is clear, everything is good. Everything is fine. Just quickly confirm once, then we will start the session. Kindly just confirm the audio video. Is it clear? Please confirm the audio video whether it is clear or not. Kindly confirm audio video is clear. Please kindly confirm audio video is clear. Yeah, I think it is fine. Yeah. So a very good evening everyone. Welcome to the energetic section of strength of material. Today we will going to see one of the most fantastic concepts that you can expect in the upcoming GATE examination. In yesterday's session, we discussed about the simple stresses and strain. We talked about stress tensor, thermal stresses, and all those questions we have discussed regarding elongation of the prismatic bar. And I told you one short trick to draw the shear force diagram. I will continue from that point itself, but before that, I would just like to make one simple announcement that, my dear, from this year onwards, we have launched this course which is called as Test Series Plus, and right now it is available to you at a discounted price of 20%, where we are providing you with India's largest test series along with the GATE question bank of technical subjects and maths and aptitude. In our GATE question bank, you can find out the detailed solution, alternate solution, key points in chapter overview, and along with that, you have a chance to get this at a discounted price of 20%. Chalo, on the same note, I would like to start my session. We were drawing the shear force diagram, and yesterday I have given you one short trick to draw the shear force diagram. So for example, if I have a overhanging beam like this, I have one overhanging beam like this. And for this overhanging beam, if I have to draw the shear force diagram, how can I proceed? So first step in drawing the shear force diagram is you need to find out the support reaction. So this is an overhanging beam which is subjected to a UDL over its entire length. This is an overhanging beam which is subjected to a UDL over its entire length, right? This length of overhang is small a, this is L, and this is again small a. So this is A, B, C and D. So whenever you need to draw the shear force diagram, first step is you need to find out the value of support reaction. First of all, tell me how many support reaction will come over this beam. Usually whenever the student sees this overhanging beam, they start feeling discomfortable. Sir, how to deal with this overhanging beam? So my simple solution will be, first of all, how many support reactions? So you have one vertical reaction VB here, one horizontal reaction HB here, then you have one vertical reaction VC here. Okay, sir. Let me take the values also. So this intensity of UDL is given to you as 10 kilonewton per meter, and the value of this overhang is 2 meter. This middle portion is, this is 2 meter. This middle portion is 5 meter, and again this portion is 2 meter. Okay. So this is the scenario given to you, and you need to find out the value of support reactions. So how to start? First thing is you will write down summation of horizontal forces equal to 0. So is there any horizontal force written? No. So HA will be equal to 0. HA is equal to 0. Now for calculating VB and VC, what you can do is either you can stand at this point B, or you can stand at this point C, or you can write down summation of moment about that point equal to 0. I'll prefer this point B. I will write down summation of moment about B equal to 0. Okay. The moment I write this equation, I have to stand at this point B and I have to consider the entire length of the beam. First, you observe the left side of the beam. So when you stand at this point B and observe the left side, you have this portion of UDL which is giving the anti-clockwise moment about point B, and the value of this moment will be minus 10 into 2 is the total load, and lever arm will be 1. The distance between CG of this load and point B is 1 meter. Okay, sir. Now observing the right side of the beam, in the right side of the beam, this portion of UDL is acting which is giving the clockwise moment, and the value of this moment is total load due to this UVL will be 10 into 5 plus 2, that is 7. So 10 into 7 is the total load, and the lever arm will be at a distance of 3.5 meter from your end B. So this will be the moment due to UDL, which is acting on the right side of B. The third moment will be due to VC, which will going to give the anti-clockwise moment about point B. Value will be minus VC into 5. Please calculate this value and get me the value of VC. Please calculate this and tell me what is the value of VC. Please calculate this and tell me what is the value of VC. So this will be how much? This will be 20. This will be 7, 7, 49. 49 into 5 divided by 5. So VC will be equal to, this will be 49 and this will be 4. So VC is equals to 45. Just check. Is VC is equals to 45 kilonewton? Is VC coming out 45 kilonewton? Just quickly check and tell me. Kindly confirm your answers. So total length of the beam is 9. Yeah, I think this will be 45. Now what you need to do is, you need to write down summation of vertical forces equal to 0. So when you write down summation of vertical forces equal to 0, you have VB and VC acting upwards. So I will write down plus VB plus VC. And this total UDL acting downwards. So what is the total load due to this UDL? Yeah, very good. Correct answer. 10 into this total length, which is 9 meter. So I will write down minus 10 into 9. So VC you have already calculated 45. So VB will also come out as 45 kilonewton. Our concepts, whatever we have read previously, will stay same, and using the same concept we will going to draw the shear force diagram for this beam. So we have calculated all the support reactions. Now let's draw the shear force diagram for this beam. Okay. Check this out. So this is your beam, which is subjected to UDL of intensity 10 kilonewton per meter. And simultaneously it is subjected to a vertical load of 45 support reaction, and here also it is 45 kilonewton. This length is 2 meter, this length is 5 meter, and this length is again 2 meter. Please draw the shear force diagram. I told you, wherever UDL is acting, you have to move linearly downwards or upwards. Right now UDL is acting downwards, so you need to move linearly downwards in the shear force diagram. Okay, now check this out. Over this portion of AB, right, UDL of 10 kilonewton per meter is acting downwards. So I need to move linearly down by the amount of 10 into 2. So 10 into 2 is minus 20. So this downward movement here is 10 into 2, which is 20. So the value of shear force at this point will be equal to minus 20. And this shear force diagram will be negative. So this is A, B, C and D. And intensity of UDL is 10 kilonewton per meter. Now at this point B, upward acting point load of 45 kilonewton is acting. So I need to move up by the amount of 45. The moment I need to move up by the amount of 45, what will be the value of shear force at this point? So this will be minus 20. Minus 20 plus 45 will be plus 25 kilonewton. Minus 20 plus 45 will be plus 25 kilonewton. Now over this portion BC, again your UDL is acting downward, so I need to move linearly down by how much amount? 10 into 5. So 10 into 5 is 50. So I need to move linearly down by the amount of 50. So if I move down by the amount of 50, this downward movement from here, this downward movement is 50. So if this value is 25, what will be this value? This value will be minus 25. This value will be minus 25. Okay, again, at this point of C, you have an upward acting point load of 45. So I need to move up by the amount of 45 here. So if I move up by the amount of 45 and this is 25, so this portion will be 20. This value of shear force will be 20, right? And over this portion CD, again UDL is acting of intensity 10 kilonewton and this length is 2. So the total downward movement will be 20. So my shear force diagram will close here and this is your shear force diagram for this beam. So just see, without even writing the shear force equation, we have drawn the shear force diagram, negative, positive. One more thing I would like to tell you here is, whenever the beam will be symmetrically loaded, then the total load over the beam will be shared between the two supports equally. Right now the beam is symmetrically loaded, so the total load over the beam that is coming is 10 into 9. So total UDL acting downward is 90 kilonewton. So half will be taken by this support and half will be taken by this support. That is why here you have the support reaction of 45 and 45. This point where shear force is 0 will be at the midpoint of this portion BC. Means if anybody asks you what is this value, so this value is nothing but 5 by 2, which is 2.5 meter. So from support B at 2.5 meter length, you will have the 0 value of shear force. And this is how you need to draw the shear force diagram, SFD. Okay. So I hope after drawing this shear force diagram, you have got enough confidence which will help you to draw shear force diagram in any scenario, in any kind of scenario. Let me take one simply supported beam also. For example, if you have a simply supported beam like this simply supported beam is subjected to few things. This simply supported beam is subjected to a moment. This is the moment, and value of this moment is 20 kilonewton per meter, 20 kilonewton meter, and then it is subjected to a UDL over the half of length of the beam, over half length of the beam like this, and simultaneously there is a point load acting here at 1/4 length. Okay, so let me just write this. All the distances are again 2 meter. This is 2 meter, then this is also 2 meter, then this is also 2 meter, and this is also 2 meter. Okay. A, this point is B, this point is C, this point is D, and this point is E. Step 1 is find out the support reaction. Please calculate the value of support reactions here. Quickly tell me the value of support reaction. 2 minutes of time for you. The point load acting is 50 kilonewton and the UDL is 10 kilonewton per meter. This is 50 kilonewton and UDL acting is 10 kilonewton per meter. Get me the value of support reactions first. All of you keep commenting your answers. Whatever you are getting, just keep commenting your answers. Don't worry about whether it will be correct or incorrect. I want the answers first. Take 2 minutes of time and get me the value of support reactions here quickly. Please tell me the value of support reactions. Quickly, we have to solve a lot of questions today. We have to see very important concepts of principal stresses and strain, and then we have to see a very important concept of deflection. Please go for it. Go for it. Get me the value of support reactions first. Balaji sir, keep commenting your answers. Keep commenting your answers. You need to draw the shear force diagram for this beam. Step 1 is calculate the support reactions. Keep commenting your answers. Chalo. First thing is, when you observe this beam, you have two reactions here, VA, and you have another reaction HA. Then you have one vertical reaction here, VE. Okay. So first thing that you will write is summation of horizontal forces equal to 0. So the moment I will write down summation of horizontal forces equal to 0, HA will become 0. HA will become 0. Okay. Now second thing is, you stand at this point A and write down summation of moment about A equal to 0. Summation of moment about A equal to 0. Okay. So the first moment will be this clockwise moment, value will be 20 kilonewton meter. So I will write down plus 20. The second moment will be due to this UDL, and the moment due to this UDL will be 10 into 4 multiplied by the distance between CG of this UDL and point A. And it will be it will be also a clockwise moment. So plus 10 into 4 is the total load, and lever arm will be distance of CG of this UDL to point A. So it will be, I think, 6 meters. So into 6. The third moment will be moment due to this 50 kilonewton load. Value will be 50 into 6, and again it's a clockwise moment about A. So plus 50 into 6. The next moment will be due to this VE, and the value of this moment will be VE into 8, and it will be an anti-clockwise moment about A. So I will write down minus VE into 8. Please tell me the value of VE. Please tell me the value of VE. One thing you might be noticing here, that whenever I am writing equilibrium equation, okay, I am taking clockwise moment as positive and anti-clockwise moment as negative. For me, upward forces are positive, downward forces are negative. Similarly, if I have to write down horizontal equilibrium equation, then horizontal forces acting towards right will be taken as positive, and the forces acting towards left will be taken as negative. Please calculate this VE and tell me the answer quickly. Please do the calculations and tell me what will be the value of VE. Please do the calculations and tell me what is the value of VE. So this will be V into 8 is equal to, so this is 20 plus 240, 20 plus 240 plus 300 divided by 8. Please do this. So this will be how much? This will be 260. 260 plus 300 will be 560 by 8. So VE is equals to 560 by 8. Please tell me, 8 sevens are 8 sevens are 56. So this will be how much? VE will be equal to 70 kilonewton. Just confirm this. V is 70. Kindly confirm this. Yeah, V is 70 kilonewton, right? Now you need to take summation of vertical forces equal to 0. So when you write down vertical forces, you have VA acting upwards, then you have UDL acting downwards, this point load acting downwards, and VE acting upwards. So you have VA plus VE minus total load due to UDL, which is 10 into 4. So minus 10 into 4. And you point load acting downward, which is minus 50, equal to 0. Substitute the value of VE and get me the value of VA. Very good, Harshita ma'am. 70 is the correct answer. All of you just quickly calculate this. I want VA. Please calculate this quickly. I want the value of VA. Show some energy, show something, right? We are in a moment of dealing one of the most crucial concept of strength of material that will going to help you in other subjects also. So that intent and tell me what is the value of VA quickly. Write minimum, calculate maximum. And even without calculator you can do this. Please do it. So VA will be how much? VA will be equal to, so this will be 40 and this will be 50. So 90. 90 minus 70. 90 minus 70 will be 20 kilonewton. Directly, even without calculating, using your calculator. And one more thing I would like to tell here, don't depend on your gate calculators. Very good evening, Richa. I'm telling you, don't depend on your gate calculators for all the calculation. Maximum calculation you have to do in your mind. And you have to use gate calculator only for very limited calculation. Very good, Praneet Kumar sir. Yeah, 20 is the correct answer. So VA is equals to 20. Now let's draw the shear force diagram for this beam. Check this out. How easily we will going to do this. Check this out. So first of all, VA is 20 kilonewton and it is acting upwards. VA is 20 and it is acting upwards. Check this out. So at this point A, I need to move up by the amount of 20. Okay, sir. At this point A, I need to move up by the amount of 20. Whenever concentrated movement is acting, what change it will going to do in the shear force diagram? Can anybody tell me that? If any concentrated movement is acting, what will this concentrated movement change in the shear force diagram? Can anybody tell me that? Can anybody tell me, is there any change in the shear force diagram due to the presence of concentrated movement? So between point A and B, there is no load acting. So shear force diagram will be constant. So here the shear force diagram will be constant. Now check this out. Due to this concentrated moment, there is no change. Very good answer, Praneet sir. Very good answer. So due to this concentrated moment, there will be no change in the shear force diagram, and the shear force diagram will be constant till this point C. Now from C to D, UDL is acting downward, so you need to move down by the amount of 10 into 2, which is 20 kilonewton. So here the value is here the value is 20. Between point C and D, you need to move down by the amount of 20 kilonewton. So again you will reach back here at 0. Then you have a downward acting point load of 50. So you need to move down by the amount of 50 here. Just check this out. This downward movement here is 20. So this shear force diagram will become 0 here. Then again you need to move down by the amount of 50. So shear force at this point will be minus 50. And then between point D and E, you have a downward acting UDL whose magnitude is 10 into 2. So again you need to move linearly down by the amount of 10 into 2. So this is the downward movement of 10 into 2. Check this out. This is minus 50 and again you need to move down by the amount of 20. So the value of shear force at this point will be minus 70. Then at this point you have an upward acting point load of VE whose magnitude is 70. So this shear force diagram will close at this point E. This shear force diagram will close at this point E, right? So this is how you need to move linearly for UDL, and wherever the point load is acting, you need to change the ordinate. So shear force diagram will be positive here. It is positive here, again positive here, but shear force diagram will be negative here, and I have written all the values of the ordinates. This will be 0 and this will be again 0. And this is your shear force diagram. Okay. So we have seen the case of cantilever beam, we have seen the case of overhanging beam, and we have seen the case of simply supported beam. Now it's time to think something about the bending moment diagram. What is bending moment diagram? First of all, check this out. For example, if there is a beam like this, I am drawing this to give you full clarity. Can anybody tell me how many types of moments can act over this beam? Can anybody in the audience, in the students, can tell me how many types of moments can act over this beam? How many types of moments can act over this beam? Anyone? How many types of moments can act over the beam, and for which moment we draw the bending moment diagram? Can anybody in the audience can tell me how many types of moments can act over the beam? For drawing the bending moment diagram, this should be the clarity, na? Which moment is giving the bending moment? For that, you should know how many types of moments can act over the beam. For example, if this is my x-axis, this is my y-axis, and the axis coming out of the board is z-axis. So this is x, y, and z. This is x, y, and z. Okay. If I apply a point load like this, a downward acting point load like this, okay, what will happen due to this point load? This point load will going to cause bending in the vertical plane. Please mark my words. Very good answer, Praneet sir. There, first of all, if you are applying this load, this point load will cause bending in the vertical plane. Which moment will cause this bending? Due to this point load, there will be a moment acting like this. There will be a moment acting like this. Now, what is this moment? You have to curl your fingers in the direction of moment, and the extended thumb will give you the axis about which this moment is acting. So, this moment is acting about z direction. So, this is mz. So, one thing I got to know that if the moment acts about z axis, then it will cause bending in the vertical plane. It will going to cause bending in the vertical plane. It can be either way. It can be deflecting downwards or it can be deflecting upwards. So whatever bending you see is because of this mz as of now. Okay. Now for example, if I apply any horizontal load like this, if I apply any horizontal load over the beam like this, what will happen to the beam? Observe my hand. Let me show you from this way. If I am applying one horizontal load like this, it will going to deflect the beam like this. Again the beam is bending, but this time the bending happens in the horizontal plane. Which moment will going to cause the bending? Moment like this will going to cause the bending. Now sir, which moment is this? Sir, for determining the direction of this moment, just curl your fingers along the direction of moment and the extended thumb will tell you the direction of this moment, which is my. So out of mz and my, mz causes bending in the vertical plane. My causes bending in the horizontal plane, and both of them are bending moments. The third moment that can act over any beam is if you apply a moment on the face of the beam like this. So when you apply a moment like this, and if you curl your fingers along the direction of moment, the extended thumb will point towards x direction. So this is your mx, and mx will cause twisting in the beam. Mx will not cause bending. Mx will going to cause twisting in the beam. Thank you so much, Rashmi. So you have three moments acting over the beam, and out of these three moments, two will cause the bending and one will cause the twisting. Now sir, if you need to draw the bending moment diagram, first you need to identify for which moment you will be drawing the bending moment diagram, whether it is mz or whether it is my. For mz variation, for the variation of mz along the length, there will be one bending moment diagram. For variation of my along the length, there will be another bending moment diagram. You cannot take both of them simultaneously. And if you are clear on this, you can solve one fantastic question asked for mechanical engineering in the GATE 2023 examination that we will going to see. So first thing is mx is the twisting moment. Mx is the twisting moment. Mx is the twisting moment. My is the bending moment. My is the bending moment which causes bending in the horizontal plane. Causes bending in the horizontal plane. Causes bending in horizontal plane. Causes bending in horizontal plane. Causes bending in horizontal plane. Then you have mz. MZ is also a bending moment. MZ is also a bending moment, and MZ causes bending in the vertical plane. Causes bending in the vertical plane. Causes bending in the vertical plane. For drawing the bending moment diagram, it is the variation of bending moment along the length of the beam. The sign convention that we use in drawing the bending moment diagram is sagging moment. Means if the beam deflects like this with a smile, then this is called as sagging. And sagging moment is taken as positive, and the depressing moment, which is called as hogging, is taken as negative. You can see smiling is always positive, therefore sagging is positive, and this is a way of depressing, right? So hogging is always negative. So if the loads are acting on the multiple planes, then you have to first draw the bending moment diagram for variation of MZ, and second is you need to draw the bending moment diagram for variation of MY. For that you have to read the question properly. Okay. Now let's see this. Bending moment over any section. Bending moment over any section is the summation of, or I should write down algebraic sum of moments. Algebraic sum of moments caused by the transverse loads. Algebraic sum of moments caused by the transverse loads, either on the left or right of the section. Either on left or right of the section. Either on left or right of the section. Either on left or right of the section. Please just give me 1 minute. Either on left or right of the section. Either on left or right of the section. Right of the section, and sagging moment will be positive and hogging moment will be negative. Okay. So let's see some questions. So this is the first question. The question is saying that for the overloading beam shown in the figure, the magnitude of maximum bending moment in kilonewton meter is. So you have an overhanging beam whose length is 4 meter plus 2 meter, and a point load of 20 kilonewton is acting at the free end, and a UDL is acting over this portion AB. Value is 10 kilonewton per meter. Again, for drawing the bending moment diagram, step number 1 is you need to calculate the support reaction. Please calculate the support reaction for this beam. Calculate support reaction for this beam. So you have beam like this. You have one vertical reaction here V1 and another vertical reaction here V2, and you have a point load acting here. I think the magnitude of the point load is 20 and this is 10. This is 20 kilonewton and this is 10 kilonewton per meter. This distance is 4 meter and this distance is 2 meter. You need to find out the maximum value of bending moment that will come over the beam. For that, you need to draw the bending moment diagram. Please do this. Please do this. Get me the value of support reaction for this beam. Take 2 minutes of time and do it. And please be quick here. Go for it. Go for it. Go for it. Please go for it. Keep commenting your answers. Keep commenting your answers. Okay, anyone with the answers? Support reactions? Please tell me the value of support reactions. So how to calculate the support reaction? Again, my dear, the process is same. Stand at any point. I will stand at this point A and I will write down summation of moment about point A equal to 0. So summation of moment about A equal to 0. So I will have first clockwise moment due to this UDL. Value will be 40 into 4 into 2. So 40 into 4, sorry, not 40, 10 into 4. 10 into 4 into 2. This is the clockwise moment. Second anti-clockwise moment will be V2 into 4 about point A. So minus V2 into 4. And the third moment will be due to this 20 kilonewton load. Value will be 20 into 6. So plus 20 into 6. Plus 20 into 6 equal to 0. Please get me the value of V2 from here. Please calculate V2. So V2 will be equal to, this will be how much? 80. This will be 120. So 80 plus 120. 80 plus 120 divided by 4. So this will be 200 by 4. So V2 is equals to 50 kilonewton. All of you just confirm this. V2 is coming out as 50. Kindly confirm this, whether the value of V2 is 50 or what. Please confirm this. V2 is 50. Kindly confirm this. Is V2 50 here? Please confirm this once. If V2 is 50, then you have to simply take summation of vertical forces equal to 0 to get the value of V1. So when you write down summation of vertical forces equal to 0, you have V1 acting upwards, then this UDL acting downward, value will be 10 into 4. So minus 10 into 4. And then you have V2 acting upwards. So V2 is plus 50. And then this 20 kilonewton load is acting downwards. So minus 20. Please tell me the value of V1 from here. Please calculate V1 from here quickly. Please tell me the value of V1 quickly. Quickly, please keep commenting your answers. Please keep replying. Whatever answer you are getting. What is the value of V1 from here? Please tell me. What is the value of V1? So this will be how much? This is minus 40. Minus 40 minus 20 will be minus 60. Minus 60 plus 50 will be minus 10. So V1 is equals to plus 10. V1 is equals to plus 10 kilonewton. Are you getting the same answer? V1 is plus 10. Now what you need to do after calculating the support reaction, first anywhere over this section AB, consider one section XX and all the distances will be measured from your end A. Consider one section XX like this and all the distances of this section XX will be measured from your end A. This distance, this is the distance X, okay. Now what will be the value of bending moment over this section XX? So the value of bending moment over this section XX will be equal to sagging moment due to this V1, value will be V1 into X. So for span AB, the value of bending moment over this section will be equal to V1 into X, which is a sagging moment. And second, due to this UDL, you will have the hogging moment, value will be 10 into X will be the total load, into X by 2 is the distance between CG of this UDL and this section XX. So this will be minus 10 into X square by 2. Just check this out. So bending moment over the section X is equal to, this is V1, V1 into X is 10 into X. So this is 10 into X minus 5X square. My dear, this is a parabolic variation with downward opening. How I have decided downward opening? The coefficient of X square is negative. So whenever the coefficient of X square is negative, the parabola will be a downward opening parabola. This equation is applicable only on this portion AB. So first calculate the value of bending moment at A. So for bending moment at A, substitute X is equals to 0. So at X is equals to 0, bending moment at A is equal to 0. You can substitute here. Next calculate bending moment at B. So at X is equals to 4 meter. At X is equals to 4 meter, right? You will get the value of bending moment at B. Substitute X is equals to 4 here. So the value of bending moment at B is equal to 10 into 4 minus 5 into 4 square. Please calculate this. Please tell me what is the value of bending moment at B. So this will be 24. Sorry, this will be 40. 10 into 4 is 40 and this is 5 into 16. 5 into 16 is, I guess, how much? 80. Yeah, this will be 80. So this is minus 80 here. So the value of bending moment at B is equal to minus 40 kilonewton meter. And from A to B, the variation of bending moment diagram is parabolic and it is a downward opening parabola. Just check this out. This is a downward opening parabola like this. So at point A, the value of bending moment is 0 and at point B, the value of bending moment is minus 20, I guess. This is minus 40, sorry. This is minus 40. Okay, sir. And this needs to be connected with a downward opening parabola. So this is how the variation will look like. It's a downward opening parabola. So this is how the variation will look like from A to B. And this is your bending moment diagram, right? This is positive here and then this is negative here. And after this, you have to consider one section XX on this portion BC. Consider one section XX over this portion BC. And again for this section XX, all the distances will be measured from your end A. All the distances will be measured from your end A. Check this out. So for span CB, for span CB, what I need to do is I have to stand over this section XX and I have observed the left side. Okay. The moment you will observe the left side, you will have first sagging moment due to V1. Value will be V1 into this distance X. So first moment will be V1 into X. And V1 you have already calculated, which is 10. So 10 into X will be the first moment. Second moment will be the moment due to UDL. Now this time it is tricky. moment due to UDL will be equal to 10 into 4, which is the total load, multiplied by the lever arm. So what is the lever arm? Distance between CG of this load and this section XX. And this distance is equals to, this total length is X, and this is 2 meter. The distance between CG of this UDL and point A is 2 meters. So distance between CG of this UDL and this section will be X minus 2. And this UDL will going to give you the hogging moment about this section. So the value will be minus 10 into 4 is the total load multiplied by X minus 2. Multiplied by X minus 2. This is the bending moment due to this UDL. Now third moment will be V2, and this V2 will be a sagging moment about this section. Value will be V2 into this distance, that is equal to V2 into X minus 4. So I will write down plus V2 into X minus 4. Just substitute the value of V2. So bending moment over section X is equal to 10x. This will be minus 40x plus 80. And this will be plus V2. V2 is how much? V2 is 50. So this will be plus 50x minus 200. Please tell me the answer for this. So this will be how much? This will be 50x, then this will be minus 40x, so plus 10. So plus 10 will be plus 20. So this will be 20x, and then you have 80 minus 200. So 80 minus 200 will be minus 120. So bending moment over section X on portion BC is equal to 20x minus 120. And we know that this is a straight line variation with a positive slope. So from B to C, the value of bending moment will vary linearly and it will going to increase, right? You have already found out the value of bending moment at B. Now calculate bending moment at C. So for the value of bending moment at C, you have to substitute X is equals to 6 meters. Substitute X is equals to 6 meters. So at X is equals to 6 meters, substitute here. So the value of bending moment at C will be equal to, this will be 120 minus 120. So bending moment at C is equal to 0. Bending moment at C is equal to 0, right? So just plot the bending moment diagram here. So from this point, the bending moment variation will be linear like this. Now the thing is, you need to find out the maximum value of bending moment. For maximum value of bending moment, you can see you have to use this equation and you have to differentiate this equation with respect to X. So I will write down for maximum bending moment, for BM max, d by dx of the first bending moment equation, this one. You have to do d by dx of this bending moment equation. So d by dx of 10x minus 5x square. 10x minus 5x square is equal to 0. So this will be equal to 10 minus 10x is equal to 0. Means at x is equals to 1 meter, you will get the value of maximum bending moment. Please calculate that. So BM max is equal to, this will be 10 into 1 minus 5 into 1. Please calculate this. This will be how much? This will be 5 kilonewton meter. This will be 5 kilonewton meter. Please check this out. This will be 5 kilonewton meter. Now you have to report the maximum value of bending moment. This is 5 kilonewton meter. So over this beam, positive maximum is 5 and negative maximum is minus 40. So you have to decide whether they are asking you the absolute maximum bending moment or not. If they are asking you absolute maximum bending moment, then the answer is minus 40 kilonewton meter, and that is hogging. Okay. If they are asking you maximum positive bending moment, then this is your answer. But for this beam, the answer is 40 kilonewton meter is the maximum bending moment that is coming over the beam. Okay. Chalo. So this is the bending moment diagram. It is positive here and then it is negative here, BMD. So answer for this question is minus 40, and that is 40 kilonewton meter is the absolute maximum bending moment. Chalo. Moving ahead with this, try this next question. What is this next question saying? The next question says that in a simply supported beam loaded as shown below, the maximum bending moment in Newton meter will be. So here you have a clamp which is attached over this beam, and with that clamp a load of 100 Newton is acting over the beam. Why I have included this question here is because this load first needs to be transferred at this point. You have to remove the clamp and you have to transfer this load from this point to this point. So you have arrangement like this. This is your beam and there is one clamp which is attached here like this. This is vertical reaction here and this is again a vertical reaction here. Let me name this. This is point A, this is point B, this is point C, this is point D and this point E. The distances I think is also given to you. This is 500, 500 and this is 100. Okay. This is 500 mm. So 0.5 meter. This is also 0.5 meter. And this is 0.1 meter. And a load of 100 Newton is acting like this. So first thing is you need to transfer this load from this point E to this point B. Then only you can draw the bending moment diagram for this beam. So when you transfer this load from point E to point B, at point B, first of all, a downward acting point load will come whose magnitude will be 100 Newton. So this is how you need to transfer the load. This is point A, this is the vertical reaction here. This is A, this is point C and this is your point B. Now over this point B, first of all you need to transfer this load. So you have a point load of 100 Newton. Second, due to this eccentricity, you will get one clockwise moment and the value of this moment, concentrated moment will be 0.1 into 100. So this will be 0.1 into 100 Newton meter. This moment and load will come over the beam. Now with this moment and load, you have to plot the bending moment diagram and over the beam, you need to find out which value will be the maximum value, right? I hope you can do this after this. The only catch here is you need to transfer this load from this point to this point, okay? After that, the process is simple for drawing the bending moment diagram. Let's move ahead. Coming to the question of mechanical engineering, which is asked in the year 2023. And this is a question in which you have loading in two planes. You can see here, this is a UDL acting in the vertical plane and you have a horizontal load P acting in the horizontal plane. And they are asking to draw the bending moment diagram about My and Mz. So I told you, first you need to check which load will going to give which moment. If you talk about this UDL is acting in the vertical plane. And due to this UDL, the moment that will come will be Mz. So the bending moment diagram due to this UDL will be the bending moment diagram of Mz. Similarly, this point load will be causing the bending moment diagram for My. Let's draw this. So these are the standard cases. First of all, let me consider a point load, let me consider this UDL. The UDL is acting like this. The UDL is acting like this. The magnitude of this UDL is W kilonewton per meter. Okay. Now, if you consider any section XX and for the cantilever beam, all the distances will be measured from the free end. Okay. So, what will be the value of bending moment over this section? So, bending moment over this section will be minus W into X is the total load due to UDL into X by 2. So, this will be minus W X square by 2, right? This is the moment due to UDL and you can clearly see This is a parabolic variation, and again, which type of parabola? A downward opening parabola. So when you draw the bending moment diagram for this load, when you draw the bending moment diagram for this load, the bending moment diagram will come like this. The bending moment diagram will come like this. It's a downward opening parabola and it will come like this. You can substitute the values and get the value of bending moment at different sections. So at this free end, the value of x is 0. So bending moment here will be 0. At this support end, the value of bending moment will be this total length L. So substitute x is equals to L. So this will be minus WL square upon 2. So this will be minus WL square upon 2. And this is your bending moment diagram, BMD. For which moment? For which moment? It is for MZ. This is your bending moment diagram for MZ. Reason is, vertical loading will cause movement about Z axis. And this moment will be a bending moment. So this is your bending moment diagram for MZ. Okay. Now second thing is, this horizontal load is acting outwards, right? This horizontal load is acting outwards. So it will going to deflect the beam in this direction, right? It will going to deflect the beam outwards. Okay. What you need to do is just take the beam and rotate it. Just take the beam and rotate it. Usually we have a habit to analyze the vertical loading only. So it becomes very simple. Just take the beam and rotate it. So when you rotate this beam, you will get the beam loading like this. You will get a beam loading like this. So you have a point load acting upwards here. When you rotate the beam, you have the loading like this. Okay. Now personally I know that this load will cause movement about y axis. For my convenience, I have rotated this beam. Okay. Otherwise this load was acting horizontally. The moment you will rotate the beam, this load will start acting upwards. But personally I know this load will going to cause bending in the horizontal plane. You have to analyze in the same way. Consider one section XX, again at some distance x from the free end. So what will be the bending moment over the section? So bending moment over the section x is equal to P into x, right? And it will be a sagging moment, so therefore positive. This bending moment will cause bending in the horizontal plane. Just plot the variation. So it's a straight line variation. It is a straight line variation like this. It is a straight line variation like this. The value of bending moment at x is equals to 0 is 0, and at x is equals to L, the value of bending moment is P into L, and this is positive. Why I am drawing this negative? This is positive. This is positive like this. So this is your bending moment variation, and this is positive here. The value of bending moment at x is equals to 0 is 0, and at x is equals to L, the value of bending moment is PL, and this is your bending moment diagram. This is your BMD for My. This is your BMD for My, which will cause bending in the horizontal plane. So you have two bending moment diagram based on the two different types of loading in different planes. Okay, let's move ahead with this. I hope this is clear. Just confirm this quickly whether it is clear or not. Kindly confirm quickly whether it is clear or not. Chat box is working for all of you, right? Or there is some problem with the chat box. Just quickly confirm whether chat box is there or not for you. Is it working for you? Is it active? Chat box is active. Just confirm quickly whether chat box is active for you or some problem came. Yes, sir. Okay. All of you just keep commenting on this so that even I can feel the energy that you people are learning very well. Okay. Chalo, let's quickly have the basic bending moment diagrams. For example, if you have a simply supported beam like this and it is subjected to a point load, anywhere over the beam. The value of load is W, this value of A, and this value is B. So your bending moment diagram will be like this. These basic bending moment diagram you should remember so that you can quickly solve the question whenever is asked from the simple cases. So the bending moment diagram will be like this. Bending moment diagram will be positive, and the maximum value of bending moment, which is very important. This maximum value of bending moment is WAB by L. This is your BMD for the beam. Similarly, if you have a simply supported beam which is subjected to UDL, this is a simply supported beam which is subjected to UDL like this. Intensity W kilonewton per meter. Then the bending moment diagram will be parabolic. Bending moment diagram will be parabolic like this. And the maximum value of bending moment here is WL square upon 8. The maximum value of bending moment here will be WL square upon 8. These basic bending moment diagrams are important to help you to solve the question quickly. For example, if you have a cantilever beam which is subjected to a point load, the value of this point load is W. The length of the beam is L. So the bending moment diagram will look like this. It will be a hogging moment, and this value will be minus W into L. If you have a cantilever beam which is subjected to UDL over its entire length, and this is W kilonewton per meter, then again just now we have drawn the bending moment diagram. The bending moment diagram will be parabolic and it will be a downward opening parabola. This will be a downward opening parabola and this value will be negative here. Okay. And the maximum bending moment that will come is minus W L square upon 2. And all these are your bending moment diagram for the standard cases that you should remember. BMD. The last thing that you should remember in this particular thing is this relation. If Y is the deflection, of the beam, then slope theta is equal to dy by dx. Now this slope theta is also known as flexural rotation. So anywhere in the question, if this term is written, flexural rotation means we are talking about the slope of the deflected shape, right? Check this out. For example, if I draw one beam like this quickly, and under the application of load W, if this beam deflects like this, then this is the deflection, that from initial position by how much amount the value or the position of the beam is deflecting, that is Y. The slope anywhere is nothing but dy by dx. You can see this. This deflection is the function of x. Deflection is the function of x, that is position over the beam. Second, theta slope is equals to dy by dx. Next, moment or curvature is equal to d theta by dx. So m is the moment, bending moment, and 1 by r is the curvature of the beam is equals to d theta by dx. Next, you have shear force which is equal to dm by dx, and last thing is you have dsf by dx, which is equal to minus times of intensity of loading. minus times of intensity of loading. This flow chart should be there. From this flow chart, one thing is very clear, that wherever your bending moment will be maximum, so dm by dx will be maximum, dm by dx will be equal to 0. At that location, the value of shear force will be equal to 0. So wherever bending moment is maximum or minimum, wherever bending moment is maximum or minimum, wherever bending moment is maximum or minimum, the shear force is equal to 0. Wherever the bending moment is maximum or minimum, the value of shear force is equals to 0. Okay. Chalo. After this, you have the theory of pure bending. So as per theory of pure bending, you have this fantastic equation, m upon I is equal to sigma upon y is equals to E upon R. M upon I is equals to sigma upon y is equals to E upon R. Now over the cross section, if any bending moment is acting, for example, this is my cross section, and over this cross section moment M is acting. So first of all, due to this moment M, the beam will undergo bending about neutral axis. So this is the neutral axis, and neutral axis always passes through CG of the cross section. So over this cross section, the moment acting is M, and due to this moment M, this cross section will undergo bending about neutral axis. And due to this bending, there will be the development of bending stresses in the cross section like this. And this bending stresses varies linearly. So first of all, you need to draw the bending strain distribution. So bending strain distribution will be like this. It will going to vary linearly like this. This is bending strain distribution. The maximum bending strain is coming over the extreme fibers, and at the neutral axis, the value of bending strain is 0. And from bending strain, if you calculate the bending stresses, so bending stresses will also vary linearly like this. This is bending stress distribution. So if the value of bending strain coming over the top fiber and bottom fiber are epsilon T and epsilon V, the value of maximum stress that will come at the top fiber will be equal to Young's modulus into epsilon T. And here the value of bending stress that will come over the bottom fiber is equals to E into epsilon B. And this is how your bending stress distribution takes place. It varies linearly over the cross section. The value of bending stresses at neutral axis is 0, and it will be maximum at the extreme fibers. So bending stresses is 0 at the neutral axis, and it is maximum at the extreme fiber. Thank you so much, Richa. It will be maximum at the extreme fibers. This is bending strain. And this is bending stress distribution. This is bending stress distribution. Now one more thing here, section modulus Z, section modulus Z is equal to, I upon Y max. Section modulus Z is equal to I upon Y max. And after this, the last thing is the moment of resistance. Moment of resistance is the amount of maximum resistance that can be offered by a cross section. The maximum amount of moment that can withstand by a cross section is termed as moment of resistance. So moment of resistance is equal to section modulus Z. Moment of resistance is equal to section modulus Z multiplied by the strength of the material, multiplied by sigma S, which is the strength of the material. So moment of resistance is Z into sigma S, and sigma S is the maximum stress that can withstand by the material. This is the important terms here for finding out the bending stresses. Okay. Now let's see this. You have one question for which They are saying for a given loading on a rectangular plane, concrete beam with an overall depth of 500 mm, the compressive strain and the tensile strain developed at the extreme fibers are of same magnitude of 2.5 into 10 raised power minus 4. The curvature of the beam cross section is, you need to find out curvature of the beam cross section. Take 2 minutes of time and please comment your answers in the comment box. It's a very important question which is asked in 2019 for civil. Please go for it. Please go for it. And keep commenting your answers. Keep commenting your answers. Keep commenting your answers quickly. Keep commenting your answers. Keep commenting your answers, please. Go for it, go for it. Okay. So what the question is asking? Question is asking you to find out the curvature of the beam cross section. Now sir, what is curvature? Curvature is 1 by r. So how can I calculate this? I know this equation, that is m upon I is equal to sigma upon y is equal to E upon r. Okay sir. But if I use this relation that sigma upon y is equal to, sigma upon y is equal to E upon r. Do I know the value of sigma? Do I know the value of E? I don't know the value of sigma, I don't know the value of E. But in this question, one very interesting fact is given to you. This is your cross section of depth 500 mm. The total depth of cross section is 500 mm, and this cross section is subjected to a moment which is giving you the maximum strains at the extreme fibers. Which is giving you the maximum strains at the extreme fibers. Check this out. So the strain distribution in this beam is linear. The strain distribution here is linear like this. You can check this out. This is the strain distribution. The maximum strain coming over the beam is at the extreme fibers, and the value of this strain is known to you. This is epsilon max and this is also epsilon max. And the value of epsilon max is given to you as 2.5 into 10 raised power minus 4. 2.5 into 10 raised power minus 4. So epsilon max is 2.5 into 10 raised power minus 4, right? So can I write down this epsilon max is equal to, sigma max upon E? Arey bhai, this is by the Hooke's law. Epsilon max is equals to sigma max upon E. This is by the Hooke's law I can write down. And for calculating sigma max, I require the value of Y max. So I can use this equation that sigma max upon Y max sigma max upon y max is equal to E upon R. Just rearrange the terms. So you have sigma max upon E into 1 upon y max is nothing but your 1 by R. And 1 by R is nothing but the curvature of the beam. This is the curvature of the beam. This is the curvature of the beam. Now substitute all the values. Sigma max by E, you already know, which is 2.5 into 10 raised power minus 4. So this is 2.5 into 10 raised power minus 4 divided by y max. So what is y max? From the neutral axis, the maximum distance of the extreme fiber, this is y max, which is equal to 250 mm. Now sir, how I am writing this directly? Because beta, this epsilon max and this epsilon max is same. So by similar triangles, I can write down this d1 and this will be 500 minus d1. 500 minus d1. So by symmetry, I can write down d1 will be 250. This 500 minus d1 will be also 250. So y max will be equal to 250. So this 2.5 into 10 raised power minus 4 divided by 250 is equal to 1 by R. Please calculate this value. Please calculate this value and tell me the answer. 2.5 into 10 raised power minus 4 divided by 250. And you want the answer in per meter. Now this 250 is in mm. So convert this mm into meters. So convert this mm into meters. So I will write down 1 by R is equals to 2.5 into 10 raised power minus 4 divided by 250 into 10 raised power minus 3. Now this will come out in per meter. Please calculate this. So this 10 raised power minus 3 and 10 raised power minus 4. So this will be how much? So this will be 1 by R is equal to 0.25 divided by 250. So this will be 0.01 times and this will be 10 times. So this will be 0.001 per meter. Are you getting the same answer? Please confirm quickly. Are you getting the same answer? 0.001. Are you getting the same answer? 0.001 per meter. Please confirm this quickly. Do it, please confirm it. Please confirm this, whether you are getting the same answer of curvature or not, 0.001 per meter. Yeah, so this will be 0.001 per meter. Okay, let's move ahead with this. Next is, you have a beam with a cross section given below subjected to a positive bending moment of 16 kilonewton meter acting around the horizontal axis. The tensile force acting on the hashed area is. You need to find out the tensile force acting over this hashed area. Now this type of question is one of the favorite varieties of question that can be framed from the bending stresses. Let's deal with this. So what you need to do is, the concept is very simple. This is your cross section. For this cross section, this is your hashed area. This is your hashed area. Okay, so this will be the neutral axis. The first thing that you need to do here is you need to find out the value of stresses on the extreme fibers. First thing is you need to find out the value of stresses in the extreme fiber. You can check this out. Since it's a symmetrical section, so stresses on the extreme fiber will be also same. For symmetrical section, stresses developed in the extreme fibers will be same. This is how the variation of stresses will take place. So it's a positive stress, positive movement. So positive movement will cause sagging of the upper fibers, compression in the upper fibers and tension in the bottom fibers. So this is how the bending stress distribution will going to vary. This is the bending stress distribution for this beam. Compression in the top fibers and tension in the bottom fibers. First, find out this value of sigma max. So you can use this equation, m upon I is equal to sigma max upon y max. So moment acting over the cross section is given to you as how much? Please tell me the value. So this is 16 kilonewton meter. Moment acting is 16 kilonewton meter. So I will write down 16 into 10 raised power 6 Newton mm. The bending moment of inertia about the cross section is equal to, so the width here is 100 and depth here is 150. So moment of inertia will be B into D cube divided by 12. So B is 100 and D is 150. So B is 100 and D is 150. So 100 into 150 cube divided by 12, and this will be in mm raised to the power 4. And this is equal to sigma max upon y max. And y max is equal to the maximum distance from this fiber to this fiber, which is given to you as 75 mm. This is 75, I guess. Yeah, this distance is 75. Please get me the value of this maximum bending stress coming over the extreme fiber. Please calculate this. Sigma max. Please tell me the value of sigma max here. Please calculate this sigma max and tell me. So let's simplify this first. So this will be how much? This will be 16 into 12 into 10 raised power 6 divided by, this will be 15 into 10 raised power 5. This is equals to sigma max upon 75. So 16 into 12 into 75 into 10 divided by 15. Please do this. Please calculate this and tell me the value. What is 16 into 12 into 75? So 16 into 12 into 75 into 10 by 15. Fifteen cube it is. This is 15 cube. So this is how much? 42 42.67 megapascal. So sigma max is 42.67 megapascal. That is the value of sigma max. Okay, once you calculated this value of sigma max, now what you need to do is use the similar triangles and get me the value of bending stresses at this level. That is this bottommost level of this hashed area, right? So you know this distance is 75 mm. And this distance is how much? I think it is given to you as 25 mm. Yeah, this is 25. This is 25 mm. And you need to find out the value of this sigma 1. So you can use the similar triangle sigma max upon 75 is equals to sigma 1 upon 25. So sigma max upon 75 is equal to sigma 1 upon 25. So sigma 1 is equals to sigma max by 3. Please calculate this. This is 42.67 divided by 3. Please tell me this value. 42.67 divided by 3. Please tell me the value. Today you people are not doing the calculations. Please do the calculations quickly. We need to see the concept of principal stresses and strain, and we need to see the concept of deflection of the beam. Please do the calculation. A lot of calculations will be required. Please calculate the value of sigma 1 quickly. What is 42.67 by 3? So 42.67 by 3. 14.22. So the value of sigma 1 will be 14.22 megapascal. Okay. Now once you got the value of sigma 1, what you need to do is, over this portion, the average stress is 0 plus sigma 1 by 2, and this average stress needs to be multiplied by this hashed area. So this is 50 mm, and this one is 25 mm. This one is 25 mm. This is 50, this is 25, right? So the tensile force acting over the hashed area is, so tensile force acting over the hashed area is, average stress acting over here. So average stress is 0 plus sigma 1 by 2. This is the average stress acting. Multiply by this hashed area, which is 25 into 50. Please calculate this. So this will be how much? 0 plus 14.22 divided by 2 into 25 into 50. And this will come out in newtons. Okay. This answer will come out in newtons. Please do the calculation. So 14.22 divided by 2 into 25 into 50. So this is 888.7. Sorry, this tensile force is 8887.5 Newton. So in kilonewton, the answer will be 8.89 kilonewton. The total tensile force that will be acting over this hashed area will be 8.89 kilonewton. Okay, like this you can approach the question. Let's move ahead with this. Next is, this is the question of shear stresses, right? You can try this question by your own. I just give you one idea about shear stresses. What is the shear stress? Shear stress on any fiber at some distance y from the neutral axis is equal to V into AY bar divided by IB. This is the equation of shear stress that we will going to use to find out the value of shear stress at any distance y from the neutral axis. For example, if this is my cross section and this is the neutral axis will always pass through the CG of the cross section. neutral axis will always pass through CG of the cross section. So if I have to find out the value of shear stress at a fiber which is situated at some distance y from the neutral axis, if I want shear stress over this fiber, that is equal to total shear force V into A y bar. A is the area above the fiber till the extreme fiber, means whichever is the nearest extreme fiber to this fiber, till that you need to take the area. So this is A. This is the value of A, right? This is A. And y bar is the distance between CG of this area to the neutral axis. This is y bar. This is A and this is y bar. Distance between CG of this area to the neutral axis is y bar. I is the moment of inertia of the cross section about neutral axis, and B is the width of the section at this fiber. Means here if you have a cross section of width B and depth D, what will be the value of small b? Here if you have a section of width B and depth D, right? So what will be the value of this small b? Right now at this section, at this fiber, the value of small b will be equal to capital B, okay, because the width is uniform. Now here one thing is, shear stress is inversely proportional to the width of the section. Shear stress is inversely proportional to the width of the section. If width of the section will going to reduce, shear stress will going to increase. But if the width of the section will going to increase, shear stress will going to reduce. Yeah, very good Harshita, very good, correct answer. 888.7.5. We are talking about the shear stress, right? Shear stress for a rectangular cross section varies parabolically, and on the extreme fibers the value of shear stress will be 0. The maximum shear stress that we will get is at the neutral axis. So this is the variation of shear stress. This is the variation of shear stress, and you will have maximum shear stress at the neutral axis, and on the extreme fibers the value of shear stress will be 0. So here you will get the maximum shear stress, and on the extreme fibers the value of shear stress will be 0. So this is the shear stress distribution for this beam. This is shear stress distribution. This is the shear stress distribution of the beam, right? You can check this out. Okay. Here is one question which says that a symmetric I section with width of each flange 50 mm, thickness of each flange 10 mm, depth of web is 100 mm, and the thickness of web is 10 mm of steel is subjected to a shear force of 100 kilonewton. Find the magnitude of the shear stress in Newton per mm square in the web at its junction with the top flange. Okay. So first of all, let's draw this I section. So you have a symmetrical I section like this. This width is 100 mm. The thickness of this flange is 10 mm. This length is 100 mm. And the thickness of this web is 10 mm. This is again 100 mm. And this thickness is 10 mm. Okay. Now since the section is symmetrical, the first thing is neutral axis will pass through the CG of this central rectangle. The neutral axis will pass through the CG of this central rectangle, the middle rectangle. The neutral axis will pass through the CG of this middle rectangle. Okay, sir. What they are asking? They want you to find out the value of shear stress, magnitude of shear stress in the junction of web at its junction with the top flange. means they want you to find out the value of shear stress over this fiber. They want you to find out the value of shear stress over this fiber. Now, first of all, what is the distance of this fiber from this neutral axis? So, depth of neutral axis will be 10 plus 100 by 2. So, this depth will be 60. From here to here, the depth of the neutral axis will be 60 mm. This is 60 mm. Okay. From here to here, this will be 50 mm. Okay, sir. You need to find out the shear stress at this junction. So, shear stress at this junction, tau, is equal to V into AY bar upon IB. So, 1 by 1. First of all, what is the value of A? So, the value of A is the area from the fiber till the top fiber. This area is A. This area is A. And what is the value of this area? Area is equal to 100 into 10 is the area. So, A is 100 into 10 mm square. Second, what is Y bar? Y bar is the distance between CG of this area till the neutral axis. So, CG of this area will be 5 mm from the top fiber. So, this distance from this fiber, from this to this neutral axis will be, this total depth is 60. 60 minus 5 will be 55. So, Y bar will be equal to 55. This is Y bar. So, Y bar is equal to 55 mm. Okay, sir. What is the width of the fiber? Width of the fiber here is 10 mm. So, small b is given to you as 10 mm. Okay, sir. Now, next is calculating moment of inertia about neutral axis. So, moment of inertia about neutral axis is moment of inertia of this first rectangle about neutral axis plus moment of inertia of this second rectangle about neutral axis and moment of inertia of this third rectangle about neutral axis. So, moment of inertia about neutral axis is moment of inertia of the first rectangle plus moment of inertia of the second rectangle plus moment of inertia of the third rectangle about neutral axis. About neutral axis. Check this out. Now, for writing the moment of inertia of this first rectangle about neutral axis, what you need to do is first, so moment of inertia of the first rectangle about neutral axis is equal to moment of inertia of this first rectangle about CG, its own CG. So, you will draw one axis like this which is parallel to the neutral axis and you will write down moment of inertia of this rectangle about this centroidal axis plus A area of this rectangle into x square. This is x1. This distance is x1. Parallel axis theorem plus A1 into x1 square. Substitute all the values. So, this will be 100 into 10 cube divided by 12 plus A1 into x1 square. So, A1 is 100 into 10 and x1 will be how much? X1 will be 55 square. Please calculate this moment of inertia about the first rectangle or moment of inertia of the first rectangle. Please calculate this moment of inertia of the first rectangle. Do it quickly. So, this will be so this will be 3033. Please tell me this moment of inertia. Kindly confirm this value. Are you getting the same answer? Please confirm this value for moment of inertia. Kindly confirm this moment of inertia. 100 into 10 cube upon 12 plus 100 into 10 into 55 square. Now second, this rectangle, the centroidal axis of this rectangle, which will be parallel to neutral axis, is overlapping with neutral axis, right? This is only the CG of middle rectangle. So what will be the moment of inertia about CG, or moment of inertia of the second rectangle about neutral axis? Moment of inertia of second rectangle about neutral axis will be equal to 10 into 100 cube by 12. Okay, this will be 10 into 100 cube by 12. So this is 303.33 into 10 raised to power 4. Yeah, correct. 303.33 into 10 raised to power 4. Correct answer. Now calculate for this one. Tell me in 10 raised to power 4 only. Tell me this answer in also 10 raised to power 4. Please tell me this answer also in 10 raised to power 4. Please tell me this answer also in 10 raised to power 4. This will be 83.33 into 10 raised to power 4. Yeah, this is 83.33 into 10 raised to power 4. mm raised to power 4. Okay. Now third, moment of inertia of the third rectangle about neutral axis is equal to moment of inertia of this third rectangle about its centroidal axis parallel to neutral axis plus A3 into x3 square. So when you draw the centroidal axis of this third rectangle, which is parallel to neutral axis, it will be like this. Okay, so what will be the moment of inertia of this third rectangle about centroidal axis? So that will be 100 into 10 cube by 12. So this is equal to 100 into 10 cube by 12 plus A3. A3 is 100 into 10 and x3 is 55 again. You have to just calculate this value. So from here till this axis, the distance will be 55 mm. Just check this out. Because from here to here, the total depth is 60. 60 minus 5 will be 55 mm. Okay. Yeah, very good. So this will be also 303.33 into 10 raised to power 4 mm raised to power 4. Now calculate the total moment of inertia. Total moment of inertia about neutral axis is twice of 303.33 plus 83.33 whole multiplied by 10 raised to power 4. Please calculate this. Calculate the total moment of inertia about neutral axis. So for first and the third rectangle, moment of inertia is coming out to be same. This is 303, right? Yeah. Please do this. So this will be 689.99. Okay. So moment of inertia about neutral axis is 689.99 into 10 raised to the power 4 mm raised to the power 4. Okay. Now you know all the values, calculate the shear stress. You know all the values. Now calculate the shear stress on the fiber. So shear stress on the fiber is equal to V into AY bar upon IB. So shear stress tau is equal to shear force. The shear force over the section is given to you as how much? The shear force over the section is 100 Newton. Keep this it in mm. Sorry, keep this it in Newton. 100 kilonewton. So 100 into 10 raised to the power 3 Newton. A is, what is A? A you have calculated, it is 100 into 10, Y bar is 55. So 100 into 10 into 55. Moment of inertia is 689.99 into 10 raised to the power 4 and B is 10. Get me the value of stress, it will come out in Newton per mm square. Yeah. Please tell me the value of shear stress, and this shear stress will come out in Newton per mm square. Please calculate this. Please tell me the value of shear stress. Please tell me the value of shear stress quickly. It is coming out as 79.71. Yeah, very good, Saundarya. This is 79.71. So shear stress tau is equals to 79.71 megapascal, Newton per mm square or megapascal. This is the value of shear stress. Okay. So this is how you can deal with the questions of shear stresses also. Let me now just jump directly into the very, very important concept of principal stresses and strain. A question is there in front of you. Right now, I haven't told you anything about this concept of principal stresses and strain. Take 2 minutes of time and solve this question. The question is saying that in a two-dimensional state of stress, analyze sigma is 120 megapascal, tau is 70 megapascal. This is sigma, this is tau. Then the value of sigma x and sigma y are respectively. Please calculate this. Have 2 minutes of time, go for it. Please go for it. Yeah, very good, Archita. Correct answer for I. Now just calculate this question. You need to solve this question, okay? Now for this question, correct answer Arshita, correct answer for shear stress, it is 79.71, yeah. For solving this question, you will have two or more methods, right? Either you can apply the formulas of stresses on the oblique plane and you can solve this. We have one more easier method that will simply require the use of basics, right? First of all, you need to understand this sigma x, sigma y, this normal stress and shear stress is acting on which plane. So for that, let me draw one 3D diagram like this. This is our plane lamina. Can you see this plane lamina, right? For this plane lamina, on this plane, this particular plane, your sigma x is acting. Sigma x is acting like this. On this particular plane, this bottom plane, sigma y is acting. And over this inclined plane, you have a normal stress of sigma n and a shear stress of tau. And a shear stress of tau, right? Let me just name this. This is A, B and C, and AB is given to you as 4. So this is A, B and C. AB is 4 meter, 4 units, BC is 3 units and this AC is 5 units. Okay. You need to find out the value of sigma x and sigma y. Okay, sir. How we can calculate this without even applying the formula? How? By using the basics, how we can solve the equation. So first of all, what you need to do is, you can imagine the thickness of this lamina as 1 unit. Means thickness of all this plane, this thickness of all the plane is 1 units. All this thickness of the plane is 1 unit. All these thickness of the plane is 1 unit, right? All these thickness of the plane is 1 unit. What will be the force due to this sigma x? So force due to sigma x is Fx, and Fx is equals to sigma x into the area of this plane over which this sigma x is acting. So this is equal to AB into 1. Okay, sir. Now force due to the sigma y is stress multiplied by the area over which this sigma y is acting. So force due to sigma y is Fy is equal to sigma y into BC into 1. This is the force due to sigma y. Now force due to this normal stress sigma n will be equal to this normal stress multiplied by the area of this plane AC. So force due to normal stress sigma is equal to Fn, which is equal to sigma into AC into 1. Similarly, force due to the shear stress tau is equal to Fs, which is equal to tau into AC into 1. You can apply the equations of static equilibrium in the forces, not in the stresses. So now when you observe all these forces will look like this. All these forces will look like this. All these forces will look like this. This is your force Fx, this is your force Fy, this is your force Fs, and this is your force, this is your force Fn, and this is your force Fs. This is Fn, this is Fs, this is Fx, and this is Fy. If I say this angle is theta, right? Check this out. If I say this angle is theta, then what will be the value of this angle? This angle will be also equal to theta, and this angle will be 90 minus theta. Okay. This angle is theta, so this angle will be 90 minus theta. So I have to simply write down summation of horizontal forces equal to 0. So the moment I will write down summation of horizontal forces equal to 0, I will have summation of horizontal forces equal to 0. So I have Fx acting this side. So minus Fx. Then this Fs sine theta again acting this side. So minus Fs sine theta. Then I have this Fn sine of 90 minus theta acting this side. So plus Fn sine of 90 minus theta equal to 0. You know the value of sine theta and you know the value of cos theta. Reason is, if this is theta, this is 4, this is 3 and this is 5. So sine theta will be 3 by 5 and cos theta will be 4 by 5. Substitute all the values and get me the value of Fx. So Fx is equals to Fn cos theta minus Fs sine theta. Okay, sir. So I can write down Fx is equals to sigma x into AB. Fn is equals to sigma into AC into cos theta, and cos theta is equals to 4 by 5 plus, sorry, minus Fs. Fs is tau into AC into sine theta, which is 3 by 5. Okay, sir. Take AC common and divide here. So sigma x into AB by AC is equal to sigma into 4 by 5 minus tau into 3 by 5. And this AB by AC is nothing but cos theta, which is 4 by 5. Substitute the value of AB by AC. So sigma x into 4 by 5 is equal to, normal stress sigma is given to you as 120 and shear stress is 70. So this is 120 into 4 by 5 minus 70 into 3 by 5. Get me the value of sigma x. Please calculate and tell me the value of sigma x here. Without applying any formula, by using the mere basics, first I have written all the stresses into forces, and then I have just taken the summation of horizontal forces equal to 0 for calculating the value of sigma x. Please get me this value of sigma x. Please calculate and tell me what is the value of sigma x. Please tell me the value of sigma x. It is 67.5. Okay. So sigma x is 67.5 megapascal. Sigma x is 67.5 megapascal. Now next is, for this lamina, take summation of vertical forces equal to 0. So when you write down summation of vertical forces equal to 0, write down summation of vertical forces equal to 0. So here you can see that Fs cos theta is acting upwards, Fn cos of 90 minus theta is acting upwards, and Fy is acting downwards. So I will write down Fs cos theta plus Fn cos of 90 minus theta minus Fy is equal to 0. Substitute all the values and get me the value of Fy. So I will write down Fy is equal to Fs cos theta plus Fn sine theta. So Fy is sigma y into Bc. This is equal to Fs, which is tau into AC, and cos theta is equals to 4 by 5 plus Fn. Fn is sigma into AC, and sine theta is 3 by 5. Substitute all the values and please get me the value of sigma y. So you have sigma y. I will take out AC common, and here I have BC by AC is equal to tau is 70. 70 into 4 by 5 plus 120 into 3 by 5. This BC by AC is 3 by 5. So you have sigma y into 3 by 5 is equal to 70 into 4 by 5 plus 120 into 3 by 5. Please calculate this and solve. Please tell me the value sigma y from here. It is 213.33. So sigma y is 213.33 megapascal. Okay, sir. Now after this, just have a quick briefing here, okay? For example, if there is an element like this which is subjected to a complex state of stress, this is an element which is subjected to sigma x, sigma y. Let me take an element like this. This is an element which is subjected to sigma x, sigma y, then you have tau xy, tau yx, tau xy, tau yx. Sigma x, sigma x, sigma y, this is tau xy, this is tau yx, this is sigma y, this is tau yx, this is tau xy. For this complex state of stress, if you consider an oblique plane, right? If you consider an oblique plane which is inclined at an angle theta from the vertical, if you consider an oblique plane which is inclined at an angle theta from the vertical, this plane will experience normal stress and shear stress, tau. This oblique plane will experience normal stress and shear stress, tau. Before writing down the value of this normal stress and shear stress, what sign convention I use to write these equations are, for normal stresses, for normal stress, tensile stresses are positive. Tensile stresses are positive and compressive stresses are negative. Compressive stresses are negative. Next, if you talk about this angle theta, if this angle theta from the vertical is measured in the clockwise direction, then theta will be positive, else negative. Theta measured in clockwise direction from the vertical is positive. And if it is anti-clockwise, it is negative. If it is anti-clockwise, it is negative, right? Then next, the shear stress should be, the direction of shear stress should be considered from this reference plane. If you need to take the direction of the shear stress, it should be considered from this reference plane AB. So over the reference plane AB, if the shear stress gives the clockwise sense of rotation, over this reference plane AB, if the shear stress gives the clockwise sense of rotation, then it is taken as positive. But over this reference plane AB, if the shear stress gives the anti-clockwise sense of rotation, then it is taken as negative. If shear stress on this reference plane AB gives the anti-clockwise sense of rotation, then it is taken as negative. Now talking about this oblique plane. Over this oblique plane, if the shear stress gives the clockwise sense of rotation, then it is positive. And if it gives the anti-clockwise sense of rotation, then it is negative. So over this oblique plane, if this is my oblique plane, over this oblique plane, if the shear stress gives the clockwise sense of rotation, then it is positive. And over the oblique plane, if the shear stress gives the anti-clockwise sense of rotation, then it is negative. This is negative here, right? So using this sign convention, I can write down the value of normal stress and shear stress over this oblique plane. So using these sign conventions, I can write down like this. Using these sign conventions, I can write down normal stress on the oblique plane is normal stress on the oblique plane is normal stress on the oblique plane is equal to sigma n. Normal stress on the oblique plane, sigma n, is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta plus tau xy sin 2 theta plus tau xy sin 2 theta. This is your normal stress on the oblique plane. Similarly, shear stress on the oblique plane is shear stress on the oblique plane shear stress on the oblique plane is equal to tau is minus of sigma x minus sigma y by 2 into sin 2 theta plus tau xy cos 2 theta. Shear stress on the oblique plane is minus of sigma x minus sigma y by 2 into cos 2 theta into sin 2 theta plus tau xy cos 2 theta. You can see here, on every oblique plane, there will be one value of normal stress and shear stress. Those oblique planes over which the value of shear stress is 0 are classified as principal planes. So those oblique planes, oblique planes over which shear stress is equal to 0 are classified as principal planes. The normal stress acting over principal planes, normal stress acting over principal plane is termed as principal stresses. The normal stress acting over principal plane is termed as principal stresses. The maximum value of principal stress is called as major principal stress, sigma 1, and the minimum value of principal stress is called as minor principal stress, sigma 2. The value of sigma 1 and sigma 2 can be calculated as sigma 1 is equals to sigma x plus sigma y by 2 plus under root of sigma x minus sigma y by 2 the whole square plus tau xy square. This is the value of major principal stress, sigma 1. The minor principal stress, sigma 2, is equals to sigma x plus sigma y by 2 minus under root of sigma x minus sigma y by 2 the whole square plus tau xy square. This is the value of minor principal stress, sigma 2. After this, the location of principal plane is, so location of principal plane. Location of principal plane. So location of principal plane is, first of all, you need to understand that in 2D loading, there will be two principal planes. There will be two principal planes. There will be two principal planes. And in 3D loading, there will be three principal planes. In 3D loading, there will be three principal planes. Why I am writing this? Because this is the only part of strength of material. From the formula point of view, it is very important, because directly from these formulas, you can expect a question in the examination. So in 3D loading, there will be three principal planes, and in 2D loading, there will be two principal planes. All these principal planes will be mutually perpendicular to each other. All these principal planes will be mutually perpendicular to each other. They will be mutually perpendicular to each other. Now, if you talk about 2D loading, the location of first principal plane theta 1 is equals to 1 by 2 tan inverse of tan inverse of sigma x minus sigma y divided by 2 tau xy. This is the location of first principal plane, and the location of second principal plane theta 2 will be equal to theta 1 plus 90 degree. So this is the location of principal plane in 2D. How many principal plane in 2D will be there? There will be two principal plane in 2D, and both these principal plane will be mutually perpendicular to each other. In the same way, there will be two oblique planes which will have maximum value of shear stress. So there will be two oblique planes of maximum shear stress. There will be two oblique planes. I will write down in 2D. In 2D, there will be two oblique planes. There will be two oblique planes having maximum value of shear stress, having tau max. Okay. Now, on such planes where maximum value of shear stress you are getting, on such planes, normal stress can be or cannot be equal to 0. There is no compulsion. In principal plane, there is a compulsion that shear stress has to be 0 over principal planes. But on the plane of maximum shear stress, the value of normal stress can or cannot be equal to 0. Okay. So in 2D, you have two oblique planes having tau max. In 3D, you have three oblique planes. You have three oblique planes with tau max. You have three oblique planes having tau max, maximum shear stress. I am talking about loading, right? In 2D loading and in 3D loading, you will have, for 2D loading, there will be two oblique planes with tau max. In 3D loading, there will be three oblique planes with tau max. Now, next is location of plane of tau max. Location of plane of tau max. Location of plane of tau max. So, what is the location of plane of tau max? So, first of all, again, these two planes of maximum shear stress will be again mutually perpendicular to each other. So, here also I should write, again all these planes will be mutually perpendicular to each other. If you talk about 2D, the planes will be mutually perpendicular. If you talk about 3D, again the planes will be mutually perpendicular to each other. So, the first location of plane of maximum shear stress phi 1 is equals to 1 by 2 tan inverse of minus sigma x minus sigma y by 2 tau xy. This is the first location of plane of maximum shear stress. The second location of plane of maximum shear stress will be phi 1 plus 90 degree, because both the planes are mutually perpendicular to each other. Then the value of tau max is equal to sigma 1 minus sigma 2 by 2. And then you have normal stress on the plane of maximum shear stress. Normal stress on the plane of maximum shear stress is sigma 1 plus sigma 2 by 2. A very good note point here, that sum of normal stresses on two mutually perpendicular plane is a constant. Means you can write down sigma x plus sigma y. Sum of normal stresses on two mutually perpendicular planes. Sigma x and sigma y are mutually perpendicular planes. This will be equal to sigma 1 plus sigma 2, and this will be equal to sigma theta on the oblique plane inclined at theta plus sigma 90 plus theta. This has to be constant. Okay. So these are the expressions of all the principal stresses and the maximum shear stress. Okay. In all these expressions of stresses, if you replace normal stress with normal strain and shear stress with shear strain by 2, you will get the expression for strains. In all these expressions, if you replace normal stress with normal strain and shear stress with shear strain by 2, you will get the expression for strains. So normal strain on the oblique plane will be normal strain on the oblique plane normal strain on the oblique plane epsilon n is equal to epsilon x plus epsilon y by 2 plus epsilon x minus epsilon y by 2 into cos 2 theta plus phi xy by 2 into sin 2 theta. This is the normal strain on the oblique plane. Similarly, shear strain on the oblique plane is so shear strain on the oblique plane phi by 2 is equal to minus of epsilon x minus epsilon y by 2 into cos 2 theta plus phi xy by 2 into sin 2 theta. Sorry, this is sin 2 theta here and phi xy by 2 into cos 2 theta. So I have just considered the expression for normal stress on the oblique plane and I have replaced this accordingly. Then I have considered the expression for shear stress on the oblique plane and I have replaced it accordingly, right? Similarly, your major principal strain and minor principal strains epsilon 1 2 is equals to epsilon x plus epsilon y by 2 plus minus under root of epsilon x minus epsilon y by 2 the whole square plus phi xy by 2 the whole square. And like that you can calculate the value of major and minor normal strain. Okay. Last is phi max by 2 or phi max is equals to epsilon 1 minus epsilon 2. Similarly, normal strain on the plane of phi max is equal to epsilon 1 plus epsilon 2 by 2. Just remembering these expressions, you can solve any question asked from this area of principal stresses and strain. Please check this out. The question is given to you. Please try this question. Have 2 minutes of time and go for it. Keep commenting your answer in the comment box. These values are visible to you. All these values are visible to you. So this is 6, this is 3, this is 4, this is 5, this is 45, this is 5 again, this is 4, this is 3 and this is 6. Please go for it. Please solve this. Okay, let's see this. First of all, what all things are given to us? This is a y plane. So you know the value of sigma y and you know the value of tau yx. Okay. So sigma y is 3, sigma y is 6. Sigma y is 6 and sigma y is tensile. So sigma y is given to you as 6 megapascal. Now check this out. This tau yx is 3 Newton per mm square acting in this direction. So the plane which is perpendicular to this horizontal plane, this vertical plane which is perpendicular to the horizontal plane, over this plane the shear stress that will be acting like this. This will be tau xy. This will be tau xy. And you can see this on this reference vertical plane, tau xy is giving the anti-clockwise sense of rotation. So tau xy is given to you as minus 3 megapascal. Tau xy is given to you as minus 3 megapascal. Okay, sir. Then an oblique plane is given to you, and this oblique plane is inclined at 45 degrees in the anti-clockwise direction. So the value of theta is minus 45 degrees. And over this oblique plane, the normal stress is tensile. So I will write down normal stress on the oblique plane is 5 megapascal. Very good, Saundarya, correct answer. Then you can see this, the shear stress on the oblique plane is giving the anti-clockwise sense of rotation. So the value of shear stress on this oblique plane is minus 4 megapascal. So tau is minus 4 megapascal. Now what you need to find out? You need to find out the maximum principal stress for this element. Okay. For calculating maximum principal stress, you require the value of sigma x. So first, either you can use the expression of normal stress or shear stress on the oblique plane, calculate the value of sigma x. I will go with this. Shear stress on the oblique plane is minus of sigma x minus sigma y by 2 into sine 2 theta plus tau xy cos 2 theta. Okay, sir. Substitute the values. So tau is minus 4. Sigma x you need to find out. So this is minus of sigma x. Sigma y is 6. So sigma x minus 6 whole divided by 2 into sine of 2 times of minus 45 degrees. So this will be sine 2 theta will be, this will be sine of minus 90 degrees. Tau xy is negative minus 3 into cos of minus 90 degrees. So first of all, cos of minus theta will be cos theta and cos 90 will be 0. So this term will be 0. Sine of minus theta will be minus sine theta. So this minus sign will come out and it will going to cancel with this minus sign. Get me the value of sigma x first. And sine 90 will be 1. So this will be equal to minus 8 is equal to sigma x minus 6. So the value of sigma x will be how much? Sigma x will be minus 2 megapascal. Are you getting sigma x as minus 2 megapascal? Just tell me. Is the value of sigma x that you are getting is minus 2 megapascal? Please confirm it once. Is it minus 2 megapascal? Saundarya ma'am, Harshita ma'am, kindly reply quickly. Is the value of sigma x that we are getting is minus 2 megapascal? Okay. Now once you got the value of sigma x, you can find out the value of maximum principal stress, that is sigma 1. So sigma 1 is equals to sigma x plus sigma y by 2 plus under root of sigma x minus sigma y by 2 the whole square plus tau xy square. So sigma 1 is equal to sigma x is minus 2, sigma y is 6. So minus 2 plus 6 plus under root of minus 2 minus 6 by 2 the whole square, and tau xy is minus 3 square. Get me the value of this sigma 1. Please tell me the value of the sigma 1. Please tell me this value of sigma 1. What will be the value of sigma 1? Quickly, everyone reply on this. Do it, do it. Please do it. Please tell me what will be the value of sigma 1. So sigma 1 is equal to, this will be 4 by 2, 2 plus under root of, this will be how much? 8 by 4, 4. So this is 16 plus 9. Seven megapascal is the correct answer. Very good, Saundarya. Correct answer. Let's move ahead with this. Try this next question. The question is saying that the state of stress condition in a deformable body is shown in the figure. Consider the transformation of the stress from the xy coordinate system to the xy coordinate system. The angle theta locating the x-axis is assumed to be positive. All this story is written to confuse you. In simple words, what they are asking is, they have given you the value of sigma y, they have given you the value of sigma x. They have given you the value of normal stress on this oblique plane, and they have given you the value of shear stress on this oblique plane, and they want you to find out the value of this tau xy. Okay, this is the stress situation given to you. This angle is 30 degree. This angle is 30 degrees. Sigma x is given to you. Sigma x is 40 MPa. Then sigma y is given to you. Sigma y is 35.6 MPa. Then your normal stress on the oblique plane, sigma n, is given to you as 120 MPa. And the value of shear stress on the oblique plane, this tau, is given to you as 50 MPa. Okay. They want you to find out the value of this tau xy. They want you to calculate the value of this tau xy. So this is how tau xy is. This is tau yx. And this is tau xy. Okay. First of all, you have to assume the direction of this tau xy and tau yx such that it gives the clockwise sense of rotation, but it is given in the question like this. Okay. So obviously, if you observe the reference plane this side, so tau xy will be acting upwards, giving the anti-clockwise sense of rotation. So whatever answer you will get, if you are getting the answer is negative, means this direction that is given in the question, you have to simply report that value. You don't have to take the sign. Okay. Now for calculating tau yx, you can use any of this expression. You can use shear stress on the oblique plane or normal stress on the oblique plane. First, find out the value of this theta. This theta is in anti-clockwise direction. Value will be minus 60 degree. So, theta is minus 60 degrees. I will use this equation of shear stress on the oblique plane. So, shear stress on the oblique plane is minus of sigma x minus sigma y by 2 into sine 2 theta plus tau xy cos 2 theta. Substitute the value of tau. Tau is given to you as 50, which is equal to minus of sigma x is 40, sigma y is minus 35.6 divided by 2. Sine 2 theta means sine of minus 120 degrees plus tau xy cos of minus 120 degrees. Please tell me the answer for this. What is the value of shear stress, tau? So, tau is coming as minus 96.18. Please confirm this. Everyone kindly confirm this, whether the value of shear stress, tau xy is coming how much? All of you kindly confirm this. What is the value of tau xy? Please confirm what will be the value of tau xy. So, tau xy, I am writing this as minus 96.18. Minus 96.18 is the value of tau xy. Now, what I want to say here is, this equation will assume the direction of tau xy as clockwise. Okay, on the reference plane, here this equation is written considering tau xy as clockwise. But here tau xy is acting in the anti-clockwise, so obviously you will get a negative answer. In this question, you have to simply report the magnitude of tau xy. So, tau xy is 96.81 megapascal. Okay. Chal, let's move ahead with this. Again, it's an easy question. A state of stress is given to you and you need to find out the value of normal stress. Okay. So, for this oblique plane, sigma x, sigma y is given to you. The value of sigma x is 100 MPa. And the value of sigma y is equal to minus 100 MPa. And you need to find out the normal stress on this oblique plane. This oblique plane is inclined at minus 45 degrees from the vertical. Okay. So, theta is minus 45 degrees. Simply you can use the equation sigma x, normal stress on the oblique plane is sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta plus tau xy sin 2 theta. Substitute all the values. So, normal stress on the oblique plane is sigma x is 100, sigma y is minus 100, whole divided by 2. Then you have, this is 100 plus 100 into cos of minus 90 degrees, and tau xy is not given, so tau xy is 0. So, this first term is 0, cos of 90 is also 0. So, these two terms are 0. So, the value of normal stress on the oblique plane will come out as 0. So, normal stress on this oblique plane is 0, right? Normal stress on this oblique plane is equals to 0. Let's move ahead with this. This is the next question which says that if the principal stresses in the two-dimensional case are minus 10 MPa and plus 20 MPa respectively, then the maximum shear stress at the point is. So you are given with the state of stress. So the value of sigma 1 is given to you as 20 MPa. The value of shear stress is given to you as 20 MPa, and the value of major principal stress is 20 MPa and minor principal stress is minus 20 MPa, right? So if you draw the Mohr circle for this state of stress, the Mohr circle will be like this. So this is my normal stress axis and this is the shear stress axis. So this is shear stress axis and this is normal stress axis. For the major principal plane, the point is 20, 0. The normal stress on the major principal plane is 20, 0, and the minor principal plane, the normal stress is minus 10, 0. Okay. Now, first of all, what will be the diameter of this circle? Diameter of this circle is 20. What will be the center of this circle? The center of the circle will be, the diameter of the circle will be 30, right? The diameter is 30, radius is 15. So, center of the circle will be at 5, 0 from here. It is simple geometry, you can do this. Now, taking this as a center and 15 as the radius, you can draw a Mohr circle like this. You can draw a Mohr circle like this. So diameter here is diameter of this Mohr circle is 30. So radius will be how much? Radius will be 15. And we know that maximum shear stress is equal to radius of the Mohr circle. Maximum shear stress will be the radius of the Mohr circle, and you can clearly see that these two planes are the planes of maximum shear stress, which are lying at the oppositely to the center. This is the plane of maximum shear stress and this is the plane of maximum shear stress. Coordinate of this point will be 5, 15. You need to move up by amount of 15 and coordinates of this point will be 5, minus 15. This is maximum shear stress, which is nothing but the radius of the Mohr circle. So the maximum shear stress is 15. Tau max is 15. 15 MPa. Okay. So this is how you need to draw the Mohr circle and you need to write down. Okay. Maximum shear stress is 15. Correct, Saundara. Absolutely correct answer. Please move ahead with this. Now what they are saying is, this is a question asked in civil engineering. They have given you the Mohr circle and they want you to identify this Mohr circle is for which loading. So 4 different types of loading is given to you: biaxial tension of equal magnitude, uniaxial tension, pure shear and hydrostatic stress. Okay. One by one. First of all, what is biaxial tension? Biaxial tension means over the element only sigma x and sigma y are acting and both of them are equal in magnitude. Means here the value of sigma x is sigma. The value of this sigma x is sigma. This is sigma. And here also sigma y is also sigma. This is also sigma, right? For this, you need to draw the Mohr circle. What I told you, whenever you need to draw the Mohr circle, just consider 2 planes which are mutually perpendicular to each other. So if you consider this plane AB, what will be the coordinates of this plane AB? If you consider plane AB, so over this plane AB, only normal stress sigma is acting. So the coordinates of plotting this point AB will be sigma, 0. Okay. Now you can consider this plane AC. For this plane AC, the coordinates of the point that you will get to plot in the normal and shear stress axis will be also sigma, 0. Okay, so this is for plane AC. When you plot these 2 points on the normal stress and shear stress axis, the Mohr circle that you will get will be a point circle like this. In this case, the Mohr circle will be a point circle, radius 0, center sigma comma 0. In fact, in all the planes, the value of normal stress will be 0 and the value of normal stress will be sigma and the value of shear stress will be 0. In this state of stress, all the planes will be principal planes. So this is biaxial tension of equal magnitude, right? Here Mohr circle will be a point circle. Mohr circle will be a point circle. Mohr circle will be a point circle here. So this is the first condition, biaxial tension of equal magnitude. Second one is uniaxial tension. Now for uniaxial tension, this is how your Mohr circle will look like. This is uniaxial tension. So you have only one stress, sigma acting like this. This is uniaxial tension. So this is plane AB and plane AC. For plane AB, the coordinates will be sigma comma 0 and for plane AC, the coordinates will be 0 comma 0. So you have to just plot these values in the normal stress versus shear stress axis and you have to draw the Mohr circle. These two values will be the diametrical ends of the Mohr circle. This is 0 comma 0 and this will be sigma comma 0. So this is how the Mohr circle will look like for this condition. This is shear stress, this is normal stress. Okay. The center of the Mohr circle will be at sigma by 2 comma 0 and the radius of this Mohr circle will be sigma by 2. Radius will be sigma by 2. Center at sigma by 2 comma 0. Now next is you have pure shear. The state of pure shear means this. This is your state of pure shear. Means the element is subjected to only shear stress like this. Right now over the element it is not subjected to any normal stress. But over the oblique planes there will be normal stress. Over the oblique planes there will be normal stress. So this is tau xy and this is tau yx. Again this is tau yx and this is tau xy. Okay. So for this element you have to again consider two mutually perpendicular planes. This is plane AB and plane AC. So what are the coordinates for plane AB? For plane AB, normal stress is 0, shear stress is tau xy. And for plane AC, the coordinates will be, this tau yx is acting in the negative direction. So negative means this tau yx is giving the anti-clockwise sense of rotation. Therefore, the coordinates here will be minus tau yx. And we know that tau xy is equal to tau yx. Yesterday I told you these are complementary shear stresses. So when you plot the Mohr circle for this, it will be like this. These are the 2 points. This is 0 comma tau xy and this will be 0 comma minus tau yx, and both of them will be equal and opposite. This is 0 comma minus tau yx. And this is the condition where you will get this type of Mohr circle. Okay, so under the state of pure shear, you will get this type of Mohr circle whose center will be at origin. Center will be at origin. The radius of the Mohr circle will be equal to tau xy. The radius of the Mohr circle will be equal to tau xy. The important thing here is the value of sigma 1, this is sigma 1 comma 0. So sigma 1 is equal to tau xy and this will be sigma 2 comma 0. So sigma 2 will be equal to minus tau yx. Minus tau yx. And this is the state of pure shear. And this is how the Mohr circle will look like. Please do this. Third one is the hydrostatic stress. Hydrostatic stress means, again, compressive normal stresses are acting. Here we have applied tensile normal stresses. Hydrostatic stresses means equal compressive normal stresses are acting in all the direction. And for hydrostatic also, you will get Mohr circle, which is a point circle, but it will be in the negative direction. Okay. So for this question, your option C is the correct answer. So this Mohr circle which is shown here is for the state of pure shear. Okay, sir. Let's move ahead with this. So again, they have given you one state of stress. You can see this 50-50 equal, right? Whenever you have equal stresses, equal normal stresses acting, in that case, your Mohr circle will be a point circle. And whenever your Mohr circle will be a point circle, center at 50, 0. So for this state, the Mohr circle will be a point circle. Mohr circle will be a point circle. Mohr circle will be a point circle with center at 50, 0 and radius is equals to 0. In such case, all the planes will be principal planes because all the oblique planes have zero shear stress. All the oblique planes are principal planes. All the oblique planes are principal planes. All the oblique planes are principal planes. And when all the oblique planes are principal planes, here you need to identify the maximum shear stress and the plane on which it will going to act. First of all the oblique planes will be principal plane. So maximum shear stress that will come out will be equal to 0. And it will act over all the planes that are present here. Means the answer will be the maximum shear stress is 0 and that shear stress will be acting for all the orientations. Means for all the oblique planes, the value of maximum shear stress is 0. So for this question, your option D is the correct answer. Option D is the correct answer. Let's move ahead with this next. Okay. So this is the important topic of this thing, principal stresses and strain, right? I would just like to give you one very important update here that from deflection, the most or the majority of the question will be framed from the standard results. So you should remember the standard results very well. Okay. Have this table directly. So if you have a cantilever beam, and the cantilever beam is subjected to moment M, and these are your 2 points A and B. So due to this moment M, theta B is equal to ml upon EI. Theta B is equal to ml upon EI and delta B is equal to ml square upon EI. ml square upon 2 EI. Delta B is equals to ml square upon 2 EI. Second is the cantilever beam subjected to a point load W. Subjected to a point load W, length L, flexural rigidity EI. Length of the member is L, flexural rigidity is EI. Then slope at B, theta B will be equal to WL square upon 2 EI and delta B will be equal to WL cube upon 3 EI. Delta B will be WL cube upon 3 EI. Next, if you have a cantilever beam which is subjected to UDL, of magnitude W kilonewton per meter cube. W kilonewton per meter, length of the beam is L, flexibility is EI, and these are the 2 points A and B. Then slope at B, theta B, is equal to WL cube upon 6 EI, and then you have delta B, which is equal to WL raised power 4 upon 8 EI. The last cantilever case is if you have a cantilever beam subjected to UVL like this. Here the maximum intensity of loading is W kilonewton per meter, and this is your point A and B. So theta B will be equal to WL cube upon 24 EI, and delta B is equal to WL raised power 4 upon 30 EI. These are some of the standard results that you should remember to solve the questions of slope and deflection. Okay, it's very, very important. Please have them. So let's see one question here. For example, there is a cantilever beam like this. This cantilever beam is subjected to UDL, and then it is subjected to point load, upward acting point load here. This UDL is say 30 kilonewton per meter, and this point load is 40 kilonewton. Okay, this length is 4 meters. This length is 2 meter, and this length is 2 meter. This is point A, point B, point C, and point D. The question is asking you to find out the value of slope and deflection at point D. What question says? Question is asking you to find out the value of slope and deflection at point D. Calculate slope and deflection at D. Calculate slope and deflection at D. Chalo. I am giving you 2 minutes of time. Let me see how many of you can solve this. How many of you can solve this question? Go for it. Anyone who can give me any idea how to solve this question? Which method to apply, how to solve this question? Go for it, go for it. in the examination, most of the question that you will get will be solved from the principle of superposition. Okay. Let's see how to apply principle of superposition here. You need to find out slope and deflection at point D, right? So slope and deflection at point D is the combined effect of this loading and this loading. Means I can simply write down the combined effect of this loading. Means if I draw one cantilever beam like this and I apply UDL over this 4 meter length, the remaining 4 meter like this. So first of all, this UDL will going to cause some slope and deflection at D. So what you need to do is, due to this loading, first find out the value of theta D1 and delta D1. Okay. Due to this loading, first find out the value of theta D1 and delta D1. Then you apply the second load only. You apply the second load only. So second load is acting like this. So this is 40 kilonewton. This is 2 meters. And this is 6 meters. So due to this second load, again at this point D, calculate the value of theta D2 and delta D2. Okay. The final delta and theta for this D. So theta D is the algebraic sum of theta D1 plus theta D2. Now here you need to take care of the sign of theta and delta. Similarly, final deflection delta D is equals to delta D1 plus delta D2. That is how you need to solve this. For theta, clockwise will be positive. Clockwise is positive and anti-clockwise is negative. And anti-clockwise is negative. Similarly, for deflection, upward deflection is positive and downward deflection is negative. Upward deflection is positive and downward deflection is negative. Downward deflection is negative, right? Everything is written in the board one by one. We will going to solve this. Okay. First, I will consider this portion where only UDL is acting. So this is called as the principle of superposition. By principle of superposition, I can solve this beam. First, consider only first portion. So you have this beam which is subjected to UDL like this. So this intensity of UDL is 30 kilonewton per meter. One second. So this is 30 kilonewton per meter. Okay. This length is 4 meter and this length is also 4 meter. Now check this out. This is A, this is B and this is D. Right now over this portion BD, no load is acting. So this portion BD will not experience any bending. Bending moment over this portion BD is equal to 0. So when you draw the deflected shape of the beam, this beam will going to deflect till point B, and beyond point B it will be a straight line like this. Beyond point B it will be a straight line like this. So whatever will be the slope at B, so I will write down theta B1, same will be the slope here, which is equal to theta D1. So whatever will be the slope theta B1, same will be the slope as theta D1. Now how to calculate theta B1? Just consider this as a cantilever beam from A to B and use the standard result. So theta B1 is equal to WL cube upon 6 EI, and that is clockwise. So W is 30, L is 4 cube upon 6 EI. Please calculate this and tell me the value of theta B1. Please calculate this theta B1 and tell me the value. Thank you so much, Richard. Thank you so much. Calculate theta B1 and tell me the value. What is 30 into 4 cube upon 6 EI? Please calculate this. 30 into 4 cube upon 6 EI. Please tell me the value. What is 30 into 4 cube upon 6 EI? So 30 into 4 cube by 6 CI. So this will be 4 cube into 5. So this will be 320 by EI. So theta B1 is 320 by EI. And that is also equal to theta D1. And since it's a clockwise slope, so I have taken this as positive. Theta D1 I got. Now sir, I want to find out the value of delta D1. Now you can check here. Delta D1 will be how much? So this is delta B. I will write down this as delta B1. So this is also delta B1. So delta D1 from here to here is the sum of delta B1 plus theta B1 into this distance, which is 4. If you write down tan of theta B1, it will be this by this, perpendicular by base, right? Now since theta is very small, tan theta can be written equal to theta. So I will write down this value will be equal to this length multiplied by theta B1. So this total will be delta D1. So delta D1 is downwards. So I know that this is downwards, so I will write down minus, and then it is equal to delta B1 plus theta B1 into 4. So delta B1 is equal to, this is W L raised power 4 upon 8 EI. So W is 30, L is 4. So 4 raised power 4 upon 8 EI plus theta B1. So theta B1 will be how much? 320 by EI into 4. Please tell me the value of delta D1. So this will be this will be 960 by EI. So delta D1 is minus of 960 by EI plus 320 into 4. What is 320 into 4? 320 into 4 is 1280 upon EI. Please find this out. Calculate the total. 960 plus 1280. Please give me the total for this. 960 plus 1280. So this will be 2240 by EI. So delta D1 is 2240 by EI. So we got the value of theta D1 and delta D1. Now next is consider the second load and calculate the value of theta d2 in delta d2. So the point load value is 40 kilonewton. This is 6 meter and this is 2 meter. This is A, this is C and this is D. This beam will going to deflect upwards. Now again it will going to deflect only up till point C, because this portion CD is not having any bending moment. So this CD will not going to deflect. Means this CD will not going to bend. Only portion AC will going to bend like this. Beyond portion C, the beam will be bending in a form of a straight line like this. Okay. So this is delta C2. And the slope here is in the anti-clockwise direction. So this will be theta C2. And we know that theta C2 will be equal to theta D2. So theta C2 is minus WL square upon 2EI. So W into L square, which is 6 square upon 2EI. This will be theta C2. Minus sign is because this is anti-clockwise. Please calculate this. WL square upon 2EI. So this will be 40 into 36 divided by 2. So this will be minus 720 by EI. So theta C2 is minus 720 by EI, which is also equal to theta D2. Minus 720 by EI, right? Now after this you need to find out the value of delta D2. So delta D2 is how much? From here to here, what will be the value of delta D2? You check this out. This is delta C2 and this remaining value will be how much? This remaining value will be theta C2 into 2. This remaining value will be theta C2. This remaining value will be theta C2 into 2, right? So the total value of delta D2 is equal to delta C2 plus delta theta C2 into 2. Since the deflection is happening upwards, so I have taken the plus sign here. Okay. Please substitute the value. So delta D2 is equal to delta C2. You have to just consider this AC as a cantilever beam and use the standard results. So due to point load, this deflection is WL cube upon 3EI. So W is 40, L cube is 6 upon 3EI. This is delta C2. Now theta C2 is, you have to only use the magnitude because you have already considered the direction, right? Don't confuse yourself. You have to only consider the magnitude of this theta C2, which is 720 upon EI. So 720 upon EI into 2. Please solve this. So this will be 40 into 6 into 6 into 6 divided by 3. So this is 2880. So delta D2 is 2880 upon EI. Then you have this, which is 1440 plus 1440 upon EI. Please calculate the value of delta D2. So 2880 plus 1440. 2880 plus 1440 is 4320 by EI. This delta D2 is 4320 by EI. Okay. Now once you got the value of delta D2 and theta D2, you can find out the net slope and deflection at D. So theta D is equal to theta D1 plus theta D2. So theta D1 is how much? So theta D1 is 320 upon EI. And theta D2, this is theta D2, which is equal to minus 720 upon EI. So I think theta D is equal to minus 400 upon EI. Minus 400 upon EI means the slope will be anti-clockwise. This will be theta D. Now calculate delta D. So delta D is equals to delta D1 plus delta D2. So delta D1 will be how much? Delta D1 will be 2240 by EI. So this is 2240 by EI. And what is delta D2? This delta D1 is negative, right? Yeah. This is minus 2240 by EI, sorry. This will be minus 2240 by EI. And delta D2 is plus 4320 by EI. Please calculate this. So minus 2240 plus 4320. So this is equals to 2080 by EI. Okay, so this is one of the variety question that you can expect in the upcoming GATE examination. Okay, so today we have seen almost all the important topics of strength of material, starting from principal stresses and strain. And starting from principal stresses and strain in the yesterday's session. In today's session, we talked about shear force and bending moment diagram. We talked about bending stresses and shear stresses. We talked about principal stresses and strain. And then we talked about the deflection of beam. And we have also seen one question from deflection of beam. My dear, before closing the session, I would just like to make few announcements. First of all, if you want to have the lecture PDF and if you want to enjoy the daily quizzes, you can join our Telegram group, for which the link is provided to you in the description box. We at IMS GATE Academy, we offer you 4 different types of courses where we provide 800 hours of live teaching with interaction and doubt solving. We provide you with theory and exercise book containing 4,000 practice questions, well versed in level 1, level 2 and level 3. We provide you with exclusive GATE question bank containing 33 years of GATE question, in which we provide you with a detailed solution, alternate solution, key points and chapter overview. We provide you with the flagship program of mentoring, where we are providing 12 personalized one-to-one mentoring sessions, which will help the student to stay focused and oriented in their entire GATE preparation journey. From this year onwards, we have launched an exclusive course which is called as Test Series Plus, and you can avail this program at just a discounted price of 20%. You will get a discount of 20%. In this, you will get India's largest test series along with the GATE question bank of maths aptitude and technical subject, and you can enjoy this at a discounted price of 20%. If you want to book a free counseling session, again, the link is provided to you in the description box. You can register yourself and our student advisory team can connect with you. So this is all, my dear. I hope these 2 sessions will be helpful for you. In case if you require any further help, Telegram is always open for you people, and for our enrolled student, already we have the doubt solving portal. And if you know me personally, you can text me also. So thank you so much for listening patiently. I just wish you all the best for upcoming GATE 25 examination. Please take care of your health and don't forget to attempt the test, because these 2 months is for your testing and improving based on your test. So kindly start attempting the test series, especially the full length mock test. So thank you so much. Have a great night ahead. Please take care.